In Class 9, you met irrational numbers. Now we will prove they are irrational using the Fundamental Theorem of Arithmetic. A number is irrational if it cannot be written as a fraction p over qa. Some familiar irrational numbers are the square root of 2, square root of 3, square root of 5, and pi to I. A non-terminating, non-repeating decimal is always irrational. Before proving irrationality, we need Theorem 1.2. If a prime p divides a squared, then p also divides a. The proof uses if a. Write a as a product of primes. Then a squared lists every prime twice. If p divides a squared, 50a uniqueness means p must be one of those prime factors, so p divides a whole. This theorem is the key tool for proving square roots of primes are irrational. Theorem 1.3 states that the square root of 2 is irrational. We prove by a contradiction. Assume root 2 equals a over b, where a and b are coprime integers. Squaring gives 2b squared equals a squared. So 2 divides a squared, which by Theorem 1.2 means 2 divides a I. Write a equals 2. Substituting gives b squared equals 2k squared. So 2 divides b squared, and by Theorem 1.2 again, 2 divides b. But 2 divides both a and b, which contradicts the fact that a and b are coprime. Therefore, the square root of 2 is irrational. Two key properties follow from the irrationality of square roots of prime. First, the sum or difference of a rational and an irrational number is irrational. Second, the product of a non-zero rational with an irrational is irrational. For instance, 5 plus root 2 is irrational, and 3 root 5 is irrational. The next 3 examples will prove specific cases of these properties. Let us summarize what we have learned in this section. Irrational numbers cannot be written as fractions. Theorem 1.2 connects prime divisibility with squares. Proof by contradiction shows root 2 is irrational, and the same argument works for the square root of any prime. The next examples will put these tools to work on specific expressions.